10.92 is a real thinker. Okay. So again, we're on our frictionless horizontal surface again, and we've got a string passing through a hole. You can't see the figure here, but I'll show you what it basically looks like from the top view. You've got a table. And you've got some kind of a block. And it's got a string that passes into a small hole. Okay. It's not fixed there, it's a hole. Okay. And it's originally revolving with a speed of 4 meters per second, and the initial radius is 0.8 meters. Then they say something weird happens. As it rotates, it's going to actually move. They're going to pull in the center. So this distance, 0.8, is going to get shorter and shorter and shorter. Okay. And eventually it's going to break. Okay. Eventually the string's breaking point is going to be 30 centimeters. I don't know what's the radius when it happens. So what's going to happen is that you're going to pull, and the string is going to get short. This string is going to get shorter and shorter, and eventually at some point here, the tension equals 30 newtons. The string breaks. And we want to know what's the radius at that point. What is the radius going to be? Well, let's take a look first at the force diagram, and then we'll talk about what's actually conserved. So, if you think about it first, you just think about the forces on it. Okay, it says it's frictionless, horizontal table, so we don't have to care about normal force or gravitational force. The only force we care about is the force of the string. Okay, so tension is going to pull in, and again it's going to be MA, but it's going to be a centripetal force. Remember, it's going in a circle. So tension is going to be mv squared over r. Okay. And it's rotating. Okay. But that force, remember that force we had over here that's pulling in on it, right? Okay. Well, that force is not a torque. Okay. So the inward force is not a torque because it's pulling along the radius. So the angle between the force and the radius is 0. So there's no torque for that on the tension. So there's no torque there. Okay. So what that means for us is that since there's no external torques on the system, then we can say that momentum is conserved. Angular momentum is conserved. In this case, L equals L prime. Okay. Again, it's only the block that has angular momentum, so we're just going to say that M V1 R1 equals M V2 R2. Okay. Notice it's the same mass both times because I have the same object, the block. Okay. But it's going to have different radii. The beginning, this is where it started from. And this is where it breaks. Okay. And we're going to have to combine those two things together to actually solve this, to find out what the radius is where it breaks. So I'm going to rewrite the equations again. T equals mv squared over r, and that m v1 r1 equals m v2 r2. Sorry about the v there. Okay, so you can see that the masses are going to divide out of that. That ends up being useful in other situations like planets going around in elliptical orbits. We're going to see that later. Okay, so we're going to say and or start plugging things in. So we've got 4 meters per second times 0.8 meters. Remember, those are the numbers that we're using for describing before when it first starts, equals V R. Again, I'm calling those V and R, not V2, R2 anymore, because I'm going to end up substituting them into the other equation. So I have 3.2 equals VR, V times R. And actually, I'm not that interested in velocity. I'm really interested in radius. So I'm going to substitute away velocity and say V equals 3.2 divided by R. I'm going to take this and I'm going to put it, actually, I'm going to take this and I'm going to put it over here. Okay, so let's try it. Okay, T equals M over R. I'm going to keep those like they are. 3.2 over R squared. Okay. All right. So you can see what's going to happen. We're going to have T equals M times 3.2 squared over R cubed. Okay. Which means we can rearrange the whole thing to R cubed, okay, equals M times 3.2 squared over T. So again, I'm solving for R, which is going to be the cube root. Now I'm going to substitute everything in. The mass was 0.250 kilograms. .2, and I want to point out the units for that are meters squared per second. I didn't note it over here, but it is divided by 30 newtons. Okay. And my answer ends up being 0.44. Okay. But my units end up being kilograms meters squared per second divided by kilograms meters per second squared. Okay. Well, then okay, or no, it's going to be actually going to be kilograms meters squared per second divided by kilograms meters per second squared. Then I'm taking the cube root of all that stuff, and amazingly, really, if you look at it, I end up with meters.